The moon is trying to kill you, not metaphorically. Right now, if you were standing on its surface, the moon would be attacking you in a dozen different ways simultaneously. And the worst part? It looks so peaceful from down here. And here is a question. If you could bring only 3 things to the moon to help you survive, what would they be? Let us know in the comments. I'll pin the most creative answer. Now let's begin. We've all seen images of the moon. That silvery sphere hanging in our night sky has captivated humanity for millennia. It seems so serene, so gentle, casting its soft light across Earth's landscapes. Ancient cultures worshipped it, poets romanticized it, and in 1969, when Neil Armstrong took that first small step onto its surface, the entire world watched in awe. But here's what those grainy television broadcasts didn't show you. Here's what the romantic poetry never mentioned. The moon is an absolute nightmare for anything trying to survive there. Think about Earth for a moment. Our planet is wrapped in layers of protection that we rarely think about because they work so perfectly. We have an atmosphere that shields us from radiation, burns up meteors before they reach the surface, and gives us air to breathe. We have a magnetic field generated by our planet's molten iron core, deflecting charged particles from the sun that would otherwise strip away our atmosphere and bombard us with deadly radiation. We have water that moderates temperatures, wind that distributes heat, and a comfortable gravitational embrace that keeps everything exactly where it should be. Earth is a cosmic sanctuary, a safe harbor in an incredibly dangerous universe. The moon has none of that, absolutely none of it. And that's where our story really begins. Standing on the lunar surface, you would be more exposed to the raw fury of space than almost anywhere else humans have ever been. There's no atmosphere whatsoever. None. The moon's gravity is simply too weak to hold on to gas molecules. They escape into space, leaving behind a near-perfect vacuum. This means several terrifying things happen simultaneously. First, there's no air to breathe, obviously, but more than that, there's no atmospheric pressure. Your spacesuit isn't just providing oxygen, it's maintaining pressure around your body. Without it, the liquids in your body would literally start to boil, even at normal body temperature. This process, called ebulism, would begin within 15 seconds of exposure to the lunar vacuum. But let's say you've got a spacesuit, you're protected from the vacuum. Surely you're safe now, right? Not even close, because now you have to contend with something far more insidious and far more dangerous. Radiation. Here on Earth, we're protected by something called the magnetosphere. Our planet's magnetic field extends thousands of miles into space, creating an invisible shield that deflects most of the charged particles streaming from the sun in what we call the solar wind. These particles are moving at incredible speeds, hundreds of miles per second, carrying enormous energy. When they hit Earth's magnetic field, they're redirected toward the poles, where they create the beautiful auroras we see in places like Alaska and Norway. The atmosphere then absorbs whatever radiation makes it through, filtering out harmful ultraviolet rays, X-rays, and other dangerous wavelengths. The moon has no such protection. Scientists believe the moon once had a magnetic field, billions of years ago when its interior was still molten and churning. But that field died long ago as the moon's core cooled and solidified. Today, the lunar surface is completely exposed to the full intensity of space radiation. And let me be clear about what that means. We're talking about galactic cosmic rays, particles that have been accelerated to near light speed by supernova explosions and other violent cosmic events. We're talking about solar particle events, massive eruptions from the sun that can deliver radiation doses that would be fatal within hours. According to measurements taken by China's Chang'e 4 lander, which touched down on the far side of the moon on January 3rd, 2019, radiation levels on the lunar surface are 2 to 3 times higher than what astronauts experience aboard the International Space Station. And that's during normal conditions when the sun is relatively quiet. During a solar particle event, a major solar flare or coronal mass ejection, radiation levels can spike to lethal doses in a matter of hours. If you were caught outside during one of these events, even your spacesuit wouldn't save you. You'd need to be underground, buried beneath several feet of rock to have any real protection. Now, if you're thinking, well, how bad could a little radiation really be? Let me paint you a picture. Radiation doesn't just give you a sunburn. At the cellular level, high-energy particles tear through your body, smashing into atoms and ripping electrons away. This creates what scientists call ionization, which damages DNA. Your cells have repair mechanisms, but when the damage is extensive enough, those mechanisms fail. Cells begin to die, or worse, they begin to replicate with corrupted genetic code. That's cancer. Astronauts on the moon would face significantly elevated cancer risks over their lifetimes, even from relatively short missions lasting just a few weeks. But cancer is a long-term problem. There are more immediate concerns. High doses of radiation can cause acute radiation syndrome, where your body's cells simply can't keep up with the damage. Your immune system begins to fail. You experience nausea, vomiting, and severe fatigue. Your bone marrow stops producing blood cells. Without immediate medical intervention, impossible on the moon, you would die within days or weeks. And here's the truly scary part. You can't see radiation, you can't feel it, and by the time you realize you've been exposed to a dangerous dose, the damage is already done. If this deep dive into lunar science is blowing your mind, hit that subscribe button and smash the thumbs up. Your support fuels this channel and helps me bring you more cosmic mysteries. In 2026, just recently, scientists analyzing data from China's Chang'e 4 mission published findings in Science Advances about something they call a cosmic ray cavity. They discovered that when the Earth and Moon align in certain configurations, there's actually a strange reduction in cosmic ray flux in the space between them. It's like an eerie shadow zone where the radiation patterns behave differently than expected. This suggests that galactic cosmic rays aren't as uniformly distributed as we once thought. While this might sound like good news, like maybe there are safe zones on the Moon, it actually makes things more complicated. It means radiation exposure on the Moon is less predictable than we realized, which makes it harder to plan safe mission timelines and habitat locations. And we're just getting started. Radiation is only one of the ways the Moon is trying to kill you. Let's talk about temperature, because the lunar environment takes the concept of extreme weather to an entirely different level. On Earth, our atmosphere acts like a thermal blanket, distributing heat around the planet and moderating temperature extremes. Ocean currents carry warmth from the equator toward the poles. Wind systems mix air masses. Even in the harshest deserts, where temperatures can swing from scorching hot during the day to freezing at night, these changes happen gradually over hours, giving you time to adapt or seek shelter. The Moon has none of these moderating influences. Without an atmosphere to trap and distribute heat, temperatures on the lunar surface swing wildly between extremes that would destroy most materials we use in everyday life. During the lunar day, which lasts about 14 Earth days because the Moon rotates so slowly, surface temperatures in direct sunlight can reach 260 degrees Fahrenheit. That's hot enough to boil water, hot enough to melt lead. Your spacesuit would be absorbing incredible amounts of thermal radiation, and without sophisticated cooling systems, you'd cook inside it like a potato wrapped in aluminum foil. But here's where it gets even more extreme. When the sun sets on the Moon, there's no atmosphere to retain any of that heat. It radiates directly back into space almost immediately. Temperatures plummet to minus 280 degrees Fahrenheit. We're talking about temperature swings of over 500 degrees. To put that in perspective, the coldest temperature ever recorded on Earth was minus 128 degrees Fahrenheit in Antarctica. The lunar night is more than twice as cold as the coldest place on our planet has ever been. Think about what that does to materials. Metals expand when heated and contract when cooled. On the Moon, they do this to extreme degrees, over and over again with each sunrise and sunset. This thermal cycling causes metal fatigue, creating microscopic cracks that grow larger over time until structural components fail. Seals and gaskets become brittle in the cold and might crack or lose their integrity. Electronics can malfunction. Even the regolith, the layer of dust and broken rock covering the lunar surface, responds to these temperature changes, potentially affecting the stability of anything built on top of it. The Apollo astronauts, who spent relatively short periods on the lunar surface, had to contend with these temperature extremes. Their spacesuits featured multiple layers of insulation, including an outer layer coated with reflective material to bounce away solar radiation. They had active cooling systems that circulated water through tubes woven into an undergarment, carrying heat away from their bodies. Even with all this technology, astronauts reported feeling uncomfortably hot when working in direct sunlight and uncomfortably cold when working in shadows. And they were only there for hours at a time, not the weeks or months that future lunar bases would require. Now imagine trying to build a permanent habitat in this environment. You'd need incredibly sophisticated thermal control systems, structures that could withstand 500-degree temperature swings, and backup systems for your backup systems, because failure means death. You couldn't just build a simple dome and call it home. Every component would need to be engineered to survive conditions that would tear apart most buildings on Earth within days. But let's say you've solved the radiation problem and the temperature problem. You've got a heavily shielded habitat buried underground or covered with lunar regolith. You've got thermal control systems keeping everything at a comfortable temperature. You venture outside to do some exploration, to collect samples, to set up scientific equipment. That's when you encounter something the Apollo astronauts called the most significant operational challenge of their missions. Something that sounds almost comically mundane, but turned out to be genuinely dangerous. Lunar dust? Now when I say dust, you're probably thinking of the stuff that accumulates on your furniture at home. That fluffy, innocuous material you wipe away with a cloth. Lunar dust is nothing like that. In fact, calling it dust is almost misleading because it suggests something harmless. What we're actually talking about is more like microscopic shards of glass mixed with razor blades, all carrying an electrostatic charge that makes them cling to absolutely everything. Here's why lunar dust is so different from Earth dust. On our planet, dust particles are weathered. They're tumbled by wind and water over millions of years until their edges become smooth and rounded. They're also mixed with organic material, pollen, dead skin cells, and all sorts of other components. Lunar dust has never been weathered. The Moon has no wind, no water, no weathering processes whatsoever. Instead, the lunar surface has been bombarded by micrometeorites for billions of years. These tiny space rocks slam into the surface at speeds of tens of thousands of miles per hour, pulverizing rock into incredibly fine particles with jagged, sharp edges. Under a microscope, lunar dust looks absolutely vicious. The particles are angular and irregular, covered in tiny points and edges. They're made primarily of silicate minerals, similar to volcanic glass, and they're incredibly small, with many particles measuring less than 10 micrometers in diameter. That's smaller than the width of a human hair, small enough to penetrate deep into your lungs if you breathe them in. But it gets worse. The Moon's surface is constantly being bombarded by charged particles from the Sun. This bombardment creates a static electric charge on everything, including dust particles. This charge makes the dust incredibly clingy. It sticks to spacesuits, to equipment, to visors, to absolutely everything it touches, and it's almost impossible to brush off. The Apollo astronauts found that lunar dust would cling to their suits no matter how hard they tried to clean themselves, before re-entering the lunar module. They'd bring it inside with them, where it would float around in the cabin, getting into equipment, coating surfaces, and most worryingly, getting into their lungs. Harrison Schmitt, the geologist who flew on Apollo 17, experienced what he called lunar dust hay fever. Shortly after exposure to the dust inside the lunar module, he developed sneezing, nasal congestion, sore throat, and watery eyes. His symptoms lasted for several hours before subsiding. Other Apollo astronauts reported similar reactions. They described the smell of the dust as something like spent gunpowder or the smell after fireworks had been set off. This distinctive odor was likely caused by chemical reactions occurring on the dust's surface, reactions triggered by exposure to oxygen and moisture inside the spacecraft. Now, the Apollo missions were short, just a few days on the lunar surface at most. The astronauts experienced acute symptoms that went away, but what about long-term exposure? What happens if you're breathing in microscopic glass shards for weeks or months? Scientists are genuinely worried about this. Studies of workers in industries like mining and construction have shown that long-term inhalation of fine silicate particles can cause serious lung diseases. On Earth, we call this silicosis, a condition where the lungs become scarred and inflamed, progressively losing their ability to absorb oxygen. There's no cure for silicosis. It's a permanent, often fatal condition. Would lunar dust cause something similar? Probably worse, actually. Remember, these particles are sharper and more jagged than terrestrial dust. They're also chemically reactive because they've been exposed to the solar wind, which implants atoms of hydrogen and other elements into their surface structure. When these particles enter the warm, moist environment of your lungs, they might trigger inflammatory responses that Earth dust wouldn't cause. In laboratory studies where human cells were exposed to simulated lunar dust, researchers observed significant toxic effects, including cell death and inflammatory responses. And the danger isn't limited to your lungs. Lunar dust could potentially cause problems for your eyes, irritating the cornea and potentially causing long-term damage. It could irritate your skin, possibly causing rashes or allergic reactions. There's even concern that the finest particles, if they get into your bloodstream, could affect your cardiovascular system or other organs. We simply don't know the full extent of the danger because we've never had humans exposed to lunar dust for extended periods. The dust problem extends beyond health concerns. It's also an engineering nightmare. Lunar dust got into everything during the Apollo missions. It contaminated seals and bearings, causing mechanical parts to wear out faster than expected. It scratched optical surfaces, degrading the performance of cameras and other instruments. It even affected the thermal properties of surfaces by coating them with dark, heat-absorbing material. One of the most famous incidents involved Eugene Cernan during Apollo 17. While working outside, he accidentally broke off the fender extension on the lunar rover. Without that fender, the rover's wheels kicked up enormous plumes of dust as it drove, coating Cernan and his partner in the abrasive material. They had to jury-rig a repair using duct tape and maps, but dust remained a constant problem for the rest of their mission. For future lunar missions, especially long-duration stays at permanent bases, solving the dust problem is absolutely critical. Engineers are working on various solutions. Special airlocks where astronauts could brush off dust before entering living areas. Electrostatic systems that could repel charged dust particles. New materials for spacesuits and equipment that resist dust adhesion. But here's the challenge. Whatever solutions we develop have to work in that extreme lunar environment with its radiation, temperature swings, and vacuum. It's not enough to create something that works in a laboratory on Earth. It has to function flawlessly in one of the most hostile environments humans have ever attempted to work in. Now let's talk about something that might seem less immediately dangerous than radiation or temperature extremes, but which poses serious long-term health risks: gravity, or rather the lack of it. The Moon's gravity is only 1/6 as strong as Earth's. When Neil Armstrong took his first steps on the lunar surface, he and Buzz Aldrin quickly discovered that moving around felt completely different. They bounced with each step. They had to learn a new way of walking, more of a loping gait than normal walking. It looked almost playful in the footage, astronauts hopping around like children on a trampoline. But reduced gravity isn't fun, and games when you're talking about living in it for weeks or months. Your body evolved over millions of years to function in Earth's gravity. Every system, from your cardiovascular system to your bones to your inner ear balance mechanisms, is calibrated for one standard gravitational force, 1g. When you remove most of that gravitational load, your body starts to change, and not in good ways. In microgravity aboard the International Space Station, astronauts experience significant bone loss. Without the constant mechanical stress that gravity provides, bones begin to demineralize. Calcium leaches out of the skeletal structure at a rate of about 1 to 2% per month. The bones most affected are the load-bearing ones, the spine, hips, and legs. This is essentially accelerated osteoporosis. Astronauts who spend 6 months on the ISS can lose the equivalent of several years' worth of bone density. Some of this can be recovered through intensive exercise after returning to Earth, but not all of it. The loss is real and potentially permanent. The Moon's 1/6 gravity is better than microgravity, but it's still only 1/6 of what your body needs to maintain healthy bones. Scientists honestly don't know exactly what will happen to humans who spend months or years in lunar gravity. Will the bone loss be proportionally less than in microgravity? Will it plateau at some point or continue indefinitely? These are questions we can't fully answer until humans actually try living on the Moon for extended periods. Then there's muscle atrophy. Without gravity constantly pulling on your muscles, they don't need to work as hard. Your body is incredibly efficient. It doesn't maintain tissue that isn't being used. In space, astronauts can lose up to 20% of their muscle mass within just a few weeks. Their hearts, which are also muscles, can actually shrink because they don't have to work as hard to pump blood against gravity. The Moon's reduced gravity would still require your muscles to work, but at only 1/6 the intensity. Over time, this could lead to significant weakening, making it difficult or even impossible for astronauts to readjust to Earth's gravity when they return home. Your cardiovascular system would face other challenges too. On Earth, your heart has to pump blood upward against gravity to supply your brain. In reduced gravity, this becomes much easier. Your body responds by reducing blood volume and allowing the heart to shrink slightly. Meanwhile, without gravity pulling fluids downward, body fluids shift toward the upper body and head. This is why astronauts in space often have puffy faces and experience congestion, what they call puffy face bird leg syndrome. This fluid shift can affect vision, with some astronauts experiencing changes in eyeball shape and visual acuity that can persist long after returning to Earth. There's also the issue of balance and spatial orientation. Your inner ear contains structures called otoliths, tiny calcium carbonate crystals suspended in fluid that move in response to gravity and acceleration. This is how your brain knows which way is up. In reduced gravity, these otoliths don't function the same way. Astronauts often experience disorientation and something similar to motion sickness when first exposed to altered gravity. While most adapt after a few days, the question remains: what happens to these delicate sensory systems during prolonged exposure to 1/6 gravity? Could they permanently recalibrate, making it difficult or impossible to readjust to Earth? And here's something really concerning that scientists are only beginning to understand. Recent studies of astronauts who've spent time in space have revealed changes in the brain itself. MRI scans show that extended spaceflight can cause the brain to shift slightly upward in the skull due to fluid redistribution. Some astronauts have experienced vision problems that correlate with increased pressure on the optic nerve. There's even evidence of subtle cognitive changes, though researchers are still working to understand exactly what's happening and why. If these changes occur in microgravity, what might happen in the Moon's 1/6 gravity over months or years? We're venturing into completely unknown territory regarding human physiology. Let's shift gears and talk about something that combines many of these dangers into one terrifying package: moonquakes. Yes, the Moon has quakes, and while they're different from earthquakes, they can be surprisingly powerful and long-lasting. Scientists first discovered moonquakes when Apollo astronauts deployed seismometers on the lunar surface. These instruments recorded seismic activity for years after the missions ended, revealing that the Moon is more geologically active than anyone expected. There are several types of moonquakes. Deep moonquakes occur about 430 miles below the surface and are thought to be caused by tidal forces from Earth's gravity flexing and stressing the Moon's interior. These happen frequently, with hundreds detected per year, but they're generally weak. Shallow moonquakes, however, are a different story. These occur much closer to the surface, within about 30 miles of it, and they can be surprisingly powerful, reaching magnitudes of up to 5.5 on the Richter scale. That's strong enough to cause significant damage to structures. Here's what makes moonquakes particularly scary compared to earthquakes. On Earth, seismic waves from earthquakes tend to dampen relatively quickly. The planet's warm, somewhat plastic mantle absorbs energy, and quakes typically last less than a minute. Moonquakes can last for over 10 minutes. The Moon is cold and rigid throughout, so there's very little dampening of seismic waves. They reverberate through the lunar structure like ringing a bell. Imagine being inside a lunar habitat during a shallow moonquake. The ground would shake violently for 10 minutes or more. Equipment would be thrown around. Structural integrity could be compromised, and unlike on Earth, where you might run outside to safety, on the Moon, outside means instant death. The seismic data collected by Apollo instruments revealed something else unsettling. Moonquakes aren't random. Many of them occur when the Moon is at perigee, the point in its orbit where it's closest to Earth. This is when tidal forces from our planet are strongest, literally squeezing and deforming the Moon's interior. It's a reminder that even though the Moon looks dead and unchanging from Earth, it's actually being constantly stressed by gravitational forces, building up tension that periodically releases in violent shaking. Building structures that can withstand these prolonged moonquakes adds another layer of complexity to lunar architecture. Your habitat needs to handle not just the temperature extremes, radiation, dust, and vacuum, but also the possibility of the ground shaking violently beneath it for 10 minutes at a time. Every joint, every seal, every structural component becomes a potential failure point. And remember, a failure on the Moon isn't like a building collapse on Earth, where rescue teams can arrive within minutes or hours. On the Moon, a structural failure that breaches your habitat's pressure integrity means explosive decompression, exposure to vacuum, and almost certain death before any rescue could be mounted. Now let's talk about something that sounds like science fiction but is a very real danger: meteorite impacts. On Earth, we're protected by our atmosphere, which acts like a shield, burning up the vast majority of space debris before it reaches the surface. Even relatively large objects, several feet across, typically disintegrate in the atmosphere, creating brilliant fireballs but never reaching the ground. The few that do make it through are usually slowed down significantly, reducing their destructive potential. The Moon has no such protection. Every piece of space debris, from microscopic dust grains to boulder-sized rocks that happens to be on a collision course with the lunar surface, strikes it at full cosmic velocity. We're talking about speeds of tens of thousands of miles per hour. At these velocities, even tiny particles carry enormous kinetic energy. A grain of sand hitting you at 30,000 miles per hour wouldn't just scratch your spacesuit. It would punch right through it like a bullet through tissue paper. The lunar surface shows evidence of this constant bombardment everywhere you look. Those countless craters, large and small, are impact scars accumulated over billions of years. The Moon's surface is the most heavily cratered terrain in the inner solar system because it has no atmosphere to burn up impactors and no geological activity to erase the craters once they form. Every single one represents a violent collision that excavated rock and sent debris flying. Here's the terrifying part about being on the Moon. This bombardment never stops. Right now, as you read this, micrometeorites are constantly pelting the lunar surface. Most are incredibly small, but there are a lot of them. Studies estimate that the Moon is hit by roughly 2,800 metric tons of meteoritic material every year. That's spread across the entire surface, so the chances of being hit in any given location at any given moment are extremely small. But over weeks or months of surface operations, the probability starts to add up. During the Apollo missions, astronauts were only on the surface for a combined total of about 3.5 days across all missions. The odds of a meteorite strike during such short periods were vanishingly small, and indeed, none occurred. But imagine a permanent lunar base where people are living and working for months or years. Eventually, someone's luck would run out. A micrometeorite would strike a habitat module, potentially causing a breach. Or it would hit a spacesuit during an EVA, an extravehicular activity. The result would be catastrophic. This danger isn't just theoretical. In 2013, astronomers observed a meteorite impact on the Moon that was visible from Earth. The impact, caused by a rock estimated to be about 3 feet across, created a flash of light as bright as the North Star and excavated a crater roughly 65 feet wide. The explosion released energy equivalent to 5 tons of TNT. If something like that hit near a lunar base, the damage would be devastating, potentially fatal. And larger impacts, while rarer, are entirely possible. The Moon has no defense against them whatsoever. Then there's the issue of secondary debris from these impacts. When a meteorite strikes the lunar surface at cosmic velocity, it doesn't just create a crater, it also launches material outward at high speeds. Some of this ejecta can be thrown hundreds or even thousands of miles from the impact site, falling back to the surface like deadly hail. During a significant nearby impact, you wouldn't just have to worry about the primary strike. You'd have to worry about all the rock fragments raining down around you, each one potentially lethal. Let's shift our focus to something more subtle but equally dangerous: isolation and psychology. The Moon is, on average, about 238,000 miles from Earth. That might not sound too far in cosmic terms. After all, astronauts can travel there in about 3 days. But psychologically, the Moon represents a profound isolation that humans have rarely experienced. When Apollo astronauts stood on the lunar surface, they could look up and see Earth hanging in the black sky, a beautiful blue and white sphere. It looked close enough to touch, yet it was impossibly far away. Everything they'd ever known, everyone they'd ever loved, every place they'd ever been was on that distant sphere. And if something went catastrophically wrong, there was no rescue coming. They were utterly alone. For short Apollo missions, this isolation was manageable. The astronauts were highly trained, focused on their objectives, and knew they'd be home within days. But what about living on the Moon for months? The psychological challenges would be immense. You'd be confined to relatively small habitats, seeing the same few people every day, eating the same limited selection of food, performing repetitive tasks, all while knowing that just outside your thin protective shell is an environment that would kill you in seconds. The lack of natural scenery, the absence of weather, the unchanging desolation of the lunar landscape, all of this could wear on the human psyche in ways we're only beginning to understand. Studies of people in isolated environments like Antarctic research stations or submarines have shown that prolonged isolation can lead to depression, anxiety, interpersonal conflicts, and cognitive decline. Some people experience something called the third quarter phenomenon, where psychological problems peak about 3/4 of the way through a long mission, when the initial excitement has worn off, but the end still seems far away. On the Moon, these psychological challenges would be compounded by the constant awareness of danger, the inability to go outside freely, and the knowledge that evacuation, if it were even possible, would take days. There's also the issue of communication delay. While the Moon is close enough that radio signals only take about 1.3 seconds to travel each way, giving a round-trip communication time of roughly 2.6 seconds, this is still enough to make real-time conversation with people on Earth feel awkward and disjointed. You can't have natural, flowing dialogue when there's a noticeable pause after everything you say. This might seem minor, but over time, it could contribute to feelings of disconnection and isolation. You're literally separated from the rest of humanity by a gap in time as well as space. And here's something that keeps mission planners awake at night: medical emergencies. On Earth, if you have a heart attack, a stroke, appendicitis, or any number of serious medical problems, emergency services can typically reach you within minutes. Hospitals have specialists, advanced imaging equipment, surgical facilities, and intensive care units. Even in remote locations, medical evacuation is usually possible within hours. On the Moon, you're days away from definitive medical care. If someone suffers a serious medical emergency, your options are severely limited. You'd have whatever medical equipment and supplies were brought along, operated by crew members who, while trained, aren't necessarily doctors or surgeons. Some medical procedures that are routine on Earth become nearly impossible in reduced gravity. Surgery, for instance, becomes far more complicated when blood doesn't settle and pool the way it normally does, when instruments float if you're not careful, and when you're working in a confined space with limited resources. Consider something as seemingly simple as appendicitis. On Earth, this is a straightforward surgical procedure with an excellent success rate. But on the Moon, you'd need someone capable of performing abdominal surgery, sterile operating conditions, anesthesia, surgical instruments, and post-operative care. If complications arose, if the patient went into shock or developed an infection, your treatment options would be drastically limited. The best outcome might be to stabilize the patient and attempt an emergency evacuation to Earth, but that would require at least 3 days of travel, assuming a spacecraft was ready to launch immediately. 3 days is an eternity when someone's life hangs in the balance. Then there are medical conditions we don't even fully understand yet because they only occur in reduced gravity or space environments. We mentioned the vision changes some astronauts experience. We know they happen, we know they can be serious, but we don't fully understand the mechanism or how to prevent them. What other medical mysteries await us on the Moon? What conditions might develop from long-term exposure to lunar dust, chronic low-level radiation, 1/6 gravity, or the combination of all these factors? There's also the psychological trauma of witnessing a serious accident in such an isolated, dangerous environment. If something goes catastrophically wrong, if a colleague dies in a suit breach or radiation exposure, or any of the countless ways the Moon can kill you, the survivors would have to continue living and working in that same deadly environment, potentially for weeks or months until the next Earth transfer window. The psychological impact of such trauma, combined with the inability to leave or receive proper mental health support, could be devastating. Let's talk about something that might surprise you: the lunar day-night cycle and what it does to human circadian rhythms. On Earth, we're adapted to a roughly 24-hour cycle of light and darkness. Our bodies have internal clocks, circadian rhythms that regulate sleep, hormone production, body temperature, and countless other physiological processes. These rhythms are synchronized with Earth's day-night cycle through exposure to natural light. The Moon rotates much more slowly than Earth. A complete lunar day from sunrise to sunrise takes about 29.5 Earth days. That means roughly 14 Earth days of continuous sunlight followed by 14 Earth days of continuous darkness. This is nothing like what human biology is designed for. Living in an environment with such an alien light cycle would wreak havoc on your circadian rhythms. During the lunar day, you'd be exposed to continuous sunlight for 2 weeks straight. During the lunar night, continuous darkness for 2 weeks. Your body wouldn't know when to sleep, when to wake, when to produce melatonin or cortisol. Studies of people living in polar regions during summer, when the sun doesn't set for weeks, show significant sleep disruption, mood changes, and cognitive effects. The lunar cycle is even more extreme. You might try to maintain an artificial 24-hour schedule inside your habitat using artificial lighting, but research has shown that artificial light alone isn't as effective at regulating circadian rhythms as natural sunlight. The lack of proper circadian synchronization over months could lead to chronic sleep deprivation, metabolic problems, immune system dysfunction, and increased risk of mental health issues. There's also a practical operational challenge. During the lunar night, solar panels don't work. If your base relies on solar power, which is the most practical long-term power source on the Moon, you'd need enormous battery systems to store enough energy to last through 14 days of darkness. Alternatively, you'd need nuclear power systems which bring their own complexities and risks. The lunar night also brings those extreme cold temperatures we discussed earlier. Keeping systems operational and maintaining habitable temperatures during 2 weeks of -280-degree darkness would require massive amounts of energy and incredibly robust thermal insulation. Now let's discuss something that connects to the Moon's formation and reveals just how violent its history has been, the lack of a substantial atmosphere, and what that tells us about lunar impacts. Scientists believe the Moon formed about 4.5 billion years ago from debris created when a Mars-sized object, which astronomers call Theia, slammed into the early Earth. This collision was so violent that it vaporized rock, creating a disk of debris orbiting Earth that eventually coalesced into the Moon. Think about that for a moment. Our serene, beautiful Moon was born from one of the most catastrophic impacts in the solar system's history. But the violence didn't end there. For hundreds of millions of years after its formation, the Moon endured what scientists call the Late Heavy Bombardment, a period when the inner solar system was being pummeled by asteroids and comets. These weren't little pebbles, these were massive objects some miles across, striking with enough force to excavate basins hundreds of miles wide. The dark patches you can see on the Moon with the naked eye, the features that form what we call the man in the Moon, are these ancient impact basins filled with solidified lava that flowed billions of years ago. The largest of these impact basins, the South Pole Aitken Basin, is one of the largest impact craters in the entire solar system. It's roughly 1,500 miles across and 8 miles deep. The impact that created it must have been absolutely apocalyptic, probably excavating material from deep within the Moon's mantle. If humans had been present to witness such an impact, well, they wouldn't have survived to tell about it. The energy release would have been equivalent to billions of nuclear weapons detonating simultaneously. These ancient impacts had profound effects on the Moon's geology and structure. They fractured the crust, created networks of cracks and fissures extending deep underground, and redistributed material across the surface. Some scientists believe these fractures could be locations where gases from the Moon's interior might occasionally vent to the surface, creating transient atmospheres in certain locations. These would be incredibly thin and short-lived, but they're a reminder that the Moon's interior might not be as dead as the surface appears. Speaking of the Moon's interior, let's talk about something truly eerie: lunar magnetic anomalies. Even though the Moon doesn't have a global magnetic field anymore, there are localized regions where the surface rocks are magnetized, creating patches of magnetic field strength that are sometimes stronger than Earth's magnetic field. These magnetic anomalies are scattered across the lunar surface, and scientists aren't entirely sure what created all of them. Some might be remnants from when the Moon had its own global magnetic field billions of years ago. Others might have been created by impacts. When a large asteroid or comet slams into rock at cosmic velocity, the shock wave can briefly create intense magnetic fields that become frozen into the rock as it cools. There's something genuinely unsettling about these magnetic patches. They're like ghosts of ancient catastrophes, remnants of violent events that occurred when the solar system was young and chaotic. These magnetic anomalies also have practical implications for lunar explorers. Compasses wouldn't work normally on the Moon. Navigation would rely on inertial systems, GPS-like satellite networks, or visual landmarks, and if you happen to set up equipment near one of these magnetic anomalies, it could interfere with sensitive instruments or communication systems. The Moon constantly reminds us that it's a world shaped by forces we can barely comprehend, operating on timescales that dwarf human history. Let's shift our attention to something that sounds beneficial but actually presents unique challenges: water ice on the Moon. Recent missions, including NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1, have confirmed that water ice exists in permanently shadowed craters near the lunar poles. This discovery was exciting because water is essential for human survival and can be broken down into hydrogen and oxygen for rocket fuel. The presence of lunar water could make long-term habitation and even lunar bases as refueling stations more feasible. But here's the catch: this water isn't sitting in convenient frozen lakes waiting to be scooped up. It's trapped in craters that never, ever see sunlight. These permanently shadowed regions are among the coldest places in the entire solar system, with temperatures as low as -400 degrees Fahrenheit. That's colder than the surface of Pluto. It's so cold that even volatile substances like carbon dioxide and methane freeze solid and remain stable for billions of years. Working in these permanently shadowed craters would be extraordinarily dangerous. You'd be operating in near total darkness, relying entirely on artificial lighting. The extreme cold would push spacesuits and equipment to their absolute limits. Materials that work fine at -280 degrees might become brittle and fail at -400. And remember, these craters are deep, with walls that can be hundreds of feet high. If something goes wrong, if you fall or your equipment fails, rescue would be incredibly difficult in such a confined, dark, freezing environment. Mining this water ice presents additional challenges. The ice is likely mixed with lunar regolith, not pure ice deposits. You'd need to excavate regolith, transport it to processing facilities, heat it to extract the water, purify the water, and then either use it directly or electrolyze it into hydrogen and oxygen. Each of these steps requires energy, equipment, and processes that must work flawlessly in that hostile environment. A breakdown anywhere in the chain could jeopardize the entire operation. There's also the question of what else might be frozen in these cold traps besides water. Billions of years of comet impacts and volcanic outgassing have deposited all sorts of volatile compounds on the lunar surface. In the permanently shadowed regions where nothing ever evaporates, these substances accumulate. Scientists have detected hints of ammonia, methane, carbon dioxide, and various organic compounds. Some of these could be useful resources, others might be toxic or corrosive. We won't know exactly what we're dealing with until we actually go there and analyze these deposits in detail. Now let's talk about communication and the far side of the Moon. Due to tidal locking, the same side of the Moon always faces Earth. We call the opposite hemisphere the far side, though it's often incorrectly called the dark side. It gets just as much sunlight as the near side, but it never faces Earth. This means that if you're on the far side of the Moon, you have no direct line of sight to Earth. Radio signals can't pass through solid rock, so you're completely cut off from direct communication with our planet. This isolation is both scientifically valuable and operationally terrifying. It's valuable because the far side is shielded from all the radio noise that Earth constantly broadcasts. It would be an ideal location for radio telescopes that could observe the universe at wavelengths blocked by our planet's ionosphere and radio interference. Astronomers dream of building telescopes on the lunar far side to study the cosmic dark ages, the period before the first stars formed, or to search for signals from distant civilizations without Earth's radio chatter drowning them out. But operationally, being on the far side means you're more isolated than any human has ever been. The Apollo 10, 11, 12, 13, 14, Quint 16 and 17 astronauts experienced this briefly when they orbited behind the Moon, losing all radio contact with Earth for roughly 45 minutes each orbit. They described an eerie silence, knowing that they were literally the most distant humans from Earth, with an entire planetary body blocking them from everyone else. Now imagine not orbiting, but living on the far side. You'd need relay satellites positioned at Lagrange points or in orbit around the Moon just to communicate with Earth. If those satellites failed, you'd be entirely cut off. There's something profoundly isolating about being in a place where you can't even see your home planet. The Apollo astronauts on the near side could look up and see Earth hanging in the black sky, a comforting reminder of home. On the far side, you'd see only stars and the emptiness of space. That psychological impact shouldn't be underestimated. Humans are social creatures who draw comfort from connection, even visual connection to home. The far side denies you even that. Let's discuss another often overlooked danger: electrostatic charging and plasma interactions. The Moon passes through different regions of space as it orbits Earth. Sometimes it's in Earth's magnetotail, a region where our planet's magnetic field streams away from the Sun like a wind sock. Other times it's exposed to the solar wind directly, a stream of charged particles constantly flowing outward from the Sun at speeds of several hundred miles per second. When the solar wind hits the lunar surface, which remember has no atmosphere or global magnetic field to deflect it, these charged particles interact directly with the regolith and any objects on the surface. This creates complex electrical environments. The day side of the Moon, exposed to solar ultraviolet radiation, becomes positively charged as electrons are knocked off atoms by energetic photons. The night side and permanently shadowed regions can become negatively charged as electrons from the solar wind accumulate faster than positive ions. These electrical charges can build up to thousands of volts. Imagine touching a doorknob after walking across a carpet and getting a static shock, then multiply that by 1,000. Astronauts and equipment can become charged to high voltages relative to the surrounding surface. While spacesuits are designed to be electrically insulating, repeated exposure to these potential differences could lead to electrical discharges that damage sensitive electronics or even pose a shock hazard during certain operations. The dust problem we discussed earlier is made worse by these electrical effects. Charged dust particles actually levitate above the surface, floating in a layer that extends several feet up. Apollo astronauts reported seeing what they called horizon glow, a faint luminescence visible just above the horizon before sunrise or after sunset. Scientists believe this was sunlight scattering off electrically levitated dust particles. This means you're not just dealing with dust on the ground. You're dealing with clouds of charged, abrasive particles suspended in the near vacuum around you, ready to coat anything and everything. During particularly intense solar storms, when the sun ejects massive clouds of charged particles toward the moon, these electrical effects can become even more extreme. The electrical potential differences can spike, creating stronger levitation effects and potentially causing damaging electrical discharges through equipment. Imagine being on the lunar surface when a solar storm hits. Not only would you face increased radiation exposure, but the entire electrical environment around you would go haywire, with dust clouds intensifying and static discharges crackling through your equipment. It would be like standing in the middle of an electrical storm, except there's no shelter to run to, no safe place to wait it out. Now let's talk about something that reveals just how alien the moon truly is, the behavior of volatiles and what it tells us about temperature extremes. On Earth, water exists in three familiar states: ice, liquid, and vapor. The transitions between these states are part of our everyday experience. Ice melts at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit at sea level. Simple, predictable, ordinary. On the moon, nothing is ordinary. Because there's virtually no atmospheric pressure, water can't exist as a liquid at all. It can only exist as ice or vapor. If you took a bottle of water to the lunar surface and opened it, the water wouldn't pour out normally. It would immediately start to boil and freeze simultaneously in a process called sublimation, transitioning directly from liquid to vapor and ice crystals. Within seconds, you'd be left with a bottle coated in frost as the water flash froze, while vapor molecules escaped into space. This isn't just a curiosity. It has profound implications for any systems that use fluids. Cooling systems, hydraulic systems, even simple things like storing drinking water all become engineering challenges. Everything must be kept under pressure and within strict temperature ranges, or it will either freeze solid or boil away. There's no middle ground, no room for error. The temperature extremes also affect how materials behave in ways that can be catastrophic. Many metals and alloys undergo phase transitions at extreme temperatures, changing their crystal structure and thus their mechanical properties. A metal that's strong and ductile at room temperature might become brittle and prone to fracturing at -280 degrees, or it might soften and lose strength at 240 degrees. Engineers designing lunar equipment must account for these temperature swings, selecting materials and designing structures that can handle the full range without failure. There's also a phenomenon called thermal cycling fatigue. When materials are repeatedly heated and cooled, expanding and contracting with each cycle, microscopic cracks can form and grow. Over time, this fatigue can cause structural failure, even in materials that seem perfectly fine. On the moon, where temperatures swing through more than 500 degrees every lunar day, thermal cycling would be relentless. Every joint, every seal, every structural component would be constantly flexing and stressing. Components that might last decades on Earth could fail within months on the moon simply from thermal fatigue. Let's discuss something that connects back to the moon's formation and affects its present danger: its strange internal structure. The moon is less dense than Earth, with an average density about 60% of our planet's. This tells us that unlike Earth, which has a large iron core making up about 1/3 of its radius, the moon has only a small core, perhaps just 200 to 300 miles across. The rest is mantle and crust, but here's where it gets weird. The moon's crust is thicker on the far side than on the near side. Scientists aren't entirely sure why. It might be related to how the moon formed, or it could be due to a massive impact early in lunar history. This asymmetry affects the moon's gravitational field, creating what are called mass concentrations or maskons. These are regions where the density of material below the surface is higher than surrounding areas, creating localized gravitational anomalies. These maskons were discovered the hard way during early lunar missions. Spacecraft orbiting the moon found their orbits slowly changing in unpredictable ways. They were being pulled slightly off course by these gravitational irregularities. Over time, if not corrected, these perturbations would cause orbits to become unstable, potentially resulting in spacecraft crashing into the surface. For future lunar operations involving satellites, space stations, or transfer vehicles, these gravitational irregularities pose navigation challenges that must be constantly monitored and corrected. The Moon's internal structure also affects moonquake activity. The shallow moonquakes we discussed earlier occur along the boundaries between different geological units, where stress accumulates as tidal forces flex the Moon's interior. The fact that we don't fully understand the Moon's internal structure means we can't perfectly predict where or when these quakes will occur. There could be faults, weak zones, or unstable regions beneath proposed base sites that we won't discover until instruments are placed there and seismic monitoring begins in earnest. There's also growing evidence that the Moon might not be as geologically dead as we once thought. Recent analysis of relatively young volcanic features suggests that volcanic activity might have occurred as recently as 50 million years ago, which is nothing in geological terms. Some scientists even speculate that occasional volcanic activity might still occur, perhaps deep underground where we can't detect it easily. The possibility of even minor volcanic activity near a lunar base, releasing gases or causing ground instability, is another risk factor to consider. Now let's talk about something that sounds almost like a ghost story: transient lunar phenomena, or TLPs. For centuries, amateur and professional astronomers have reported strange temporary changes on the Moon's surface: bright flashes, glowing spots, colored hazes, or areas that seem to temporarily change brightness. These reports have been controversial, with many scientists dismissing them as observational errors, atmospheric effects on Earth, or tricks of light and shadow. However, some TLP reports are backed by multiple independent observers and even photographic evidence. The most famous occurred in November 1958, when Russian astronomer Nikolai Kozyrev claimed to observe a reddish glow in the crater Alphonsus and obtained a spectrum showing gaseous emissions. While this observation remains disputed, it raised the possibility that gases might occasionally vent from the lunar interior, creating brief, localized changes in appearance. Other explanations for TLPs include meteorite impacts, which would create brief flashes of light, electrical discharges in levitated dust clouds, outgassing from the lunar interior through cracks or fissures, or even effects related to solar-wind interactions with the surface. Whatever the cause, the fact that the Moon occasionally does unexpected things is unsettling when you're planning to live there. You want your environment to be predictable and well understood. TLPs suggest there are still phenomena occurring on the Moon that we don't fully comprehend. Imagine you're inside a lunar habitat at night and you see through your viewport a strange glow appearing in a nearby crater. Is it an impact, an electrical phenomenon, outgassing? Whatever it is, it's a reminder that you're living on a world that can still surprise you. And not all surprises in space are pleasant ones. Let's discuss resource availability and what it means for long-term survival. The Moon is made largely of the same materials as Earth's mantle and crust: oxygen, silicon, aluminum, iron, calcium, magnesium, titanium. In theory, you could extract and process these elements to create building materials, metals for manufacturing, and even oxygen for breathing. Several tons of lunar regolith could be processed to extract 1 ton of oxygen, for example. If you made this far, I am sure you will love this other video at the left side of the screen. Why you wouldn't last 1 year on Mars. Here is a preview. Mars's atmosphere is 100 times thinner than Earth's. Standing on Mars equals 100,000 feet altitude, where blood literally boils without pressurized suits. See you there.